Malignant cancer cells operate in highly chaotic, non-regularizing environments, multiplying and expanding rapidly outward in 3 physical dimensions. The objective of computational oncology is predicting which specific lineage within this cluster will achieve clonal dominance. Standard models consistently fail to make this prediction. The core flaw is premature scalarization. Multidimensional cellular histories are collapsed into a flat, 2-dimensional line. Flattening this data discards essential temporal correlations. As the graph maps forward, it completely misses a newly branching subpopulation, losing the ability to track therapy-resistant states. Classical scalar methodologies replace attainable histories with isolated, independent worst-case transitions, often utilizing single-step Lyapunov bounds. Row-wise domination matrices also fail by double-spending multiplicities, a process that violates source conservation during cell division. This table contrasts heuristic, scalar methods with the structural requirements of a unified mathematical framework. Notice the shift from dual operator models to a 3-level architecture. To rigorously predict tumor population stability, we must fundamentally shift our approach and adopt the spectral geometry of the age-structured renewal operator. This operator architecture maps abstract functional analysis directly to cellular states, establishing a bridge between microscopic lineages and macroscopic mass transport. This 3-tiered diagram maps the age-structured operator as a bridge between functional analysis and observation, divided into 3 distinct mathematical levels. Isolating the bottom tier, we find T, the unfolded coordinates. This level tracks the exact granular age and lineage of individual cells. Because T preserves the exact temporal history of the cell, it prevents the data loss common in scalar models. As the view shifts to the middle tier, we reach RDOM, or folded counting. The unfolded microscopic history is structurally grouped into discrete subpopulations. This mesoscopic level connects directly to clinical practice, providing the discrete multiplicity data used in standard colony-forming assays. Finally, the cylinders dissolve into the smooth heat map of the top tier. This is P, density transport. It represents the total distribution of phenotypic traits across the tumor mass. Accurate modeling requires passing precisely through these 3 mathematical phases, rather than jumping straight from a single cell to a tumor mass. This equation, JDOM-T equals RDOM-JDOM, establishes the transition between the microscopic and mesoscopic levels as a mathematical isomorphism. This intertwining relation means that unfolded coordinates and folded cylinders represent the same biological reality. The conflict arises when transitioning from folded counting to macroscopic density, where counting metrics and continuous volume representations diverge. Simply converting discrete counts to continuous density during tumor expansion violates Lebesgue mass conservation laws. This is known as the factor of lambda discrepancy. Applying the formula 1 over lambda as a spatial filter introduces a radon-Nikodym Jacobian weighting. This synchronizes the underlying branching multiplicities with the macroscopic density. This weighting factor marks the structural divergence between counting-based and density-based representations. Without this specific Jacobian weight, models simulate phantom mass. With it, the macroscopic transport remains synchronized with the underlying cell counts. By returning to the microscopic level, we can examine how this framework predicts the survival of therapy-resistant subpopulations. Notice how all branches fade, except one continuous path. This is the deterministic spine, a lineage that avoids treatment-induced apoptosis or senescence. This spine is governed by a multiplicity-weighted countdown renewal identity, providing a growth bound for the resistant lineage. The equation R equals the ceiling of T acts as a countdown clock. It ticks downward at each node, tracking the timing of branching events. This countdown clock establishes an arithmetic bound for the growth rate of surviving lineages. Legacy scalar models fail to determine the true certificate norm of the joint age state, whereas the deterministic spine provides arithmetic precision. This mechanism ensures that surviving populations are modeled through precise growth bounds rather than statistical approximations. The final challenge is determining whether the resistant population will achieve stable dominance or fragment into diverse subpopulations. Proving L1 uniqueness is historically difficult in the highly irregular signaling environments characteristic of malignancy. Disconnected clusters of active cells form a positivity set. We use bi-Lipschitz mappings to ensure null sets remain null, demonstrating that these irregular clusters occupy the full measure of the tissue. This measure-theoretic full support avoids the fat Cantor-Seck error, proving that active tumor populations can occupy full measure without topographical continuity. We then apply structural logic to track how this unique clonal population descends. Standard models read lineage from root to tip using prefix-based logic. This often misidentifies the sequence of differentiation in branching models. The suffix rigidity theorem traces lineage backward from terminal tips toward the root, forming a rigid laminar semilattice. Cellular descent follows this reverse suffix order, which correctly resolves the sequence of differentiation. Relying on this suffix-based semilattice eliminates the order convention errors that plague other models. Combining L1 uniqueness with suffix rigidity ensures our classification of clonal cylinders matches the true biological sequence of descent. By pulling back from the microscopic cellular lattice to the macroscopic tissue mass, we see the scale of this unified framework. By applying Jacobian weighting, we resolve the divergence between counting-based representations and Lebesgue mass conservation. To move beyond descriptive models, advancing C-star algebraic oncology requires 3 strategic research imperatives. First, the field must prioritize classifying stable clonal cylinders to ensure tracking adheres to reverse suffix rules. Second, models must utilize Haar measure-based representations to faithfully audit the partial isometries of cellular growth. Third, researchers must immediately abandon scalar surrogates as they structurally violate source conservation in branching processes. The age-structured renewal operator provides the mathematical rigor required to establish population uniqueness and predict the stability of heterogeneous tumor systems.